last time the way the Raman spectrum actually originates, it's very different from all that we have learned so far. In the sense, it's very different from the absorption spectrum that we have studied for rotations and vibration rotations, because in all these cases, the spectrum was actually generated because of the dipole moment of the molecule oscillating with time. In the case of vibrations, the dipole moment changing with vibrations, and in the case of rotation, the molecule had a permanent dipole moment. I think one of the stop now. So the molecule had a permanent dipole, it was rotating. Then of course we had the dipole changing with time because the vector is actually rotating all the time, changing its direction. Then we get a changing dipole moment component of the molecule. We will see now that Raman spectra does not really depend on the dipole moment changes, it depends on something else. And that's the reason why it's very different from what we have seen before. All absorption experiments depend basically on the dipole moment component interacting with the intensity of light. Whereas in the case of Raman, it's not the dipole moment that's really interacting, it's something else that's going to be interacting. We will see what that is as we go along. But just to put the whole technique in perspective, we said what really happens is that the molecule is scattered, or the molecule scatters the photon. We have a molecule out here, a photon that goes to hits it of frequency mu and scatters off with frequency mu prime. Then mu could be equal to mu prime, in which case the molecule hasn't really taken away any energy from the photon. It's going to be lying in the same state. And the scattered photon, which is the same frequency as the original photon, you can see that it's Rayleigh scattering, and it happens most of the time. Whereas if you do Raman spectra, and if you have this mu prime different from mu double prime, or mu prime different from initial mu, then of course there's something else happening. Part of the energy from the photon has actually been absorbed by the molecule, and therefore you will find that the molecule has changed its state. It's going to be in a different state than what it was originally. And there of course you have a situation in which you start getting information about the state of the molecule, or the vibration energy, or the rotation energy of the molecule. Now that I think the class has come in bigger numbers and most of you have settled in, we have the usual ritual to do. I think 20th. Today I think it's Friday time. And of course the question is who you share it with. It's with James Dewar. James Dewar is actually a person who specialized in low temperature science. He was the one who showed that he could liquefy air and nitrogen with hydrogen, and he basically did a lot of work on production of cryogenic liquids, which of course was very important in a lot of other sciences, particularly in superconductivity. And that's what Dewar did. And he also designed vessels in which you can hold these liquids for long periods of time, and these are called Dewar flasks or Dewar containers. And we just come up with the chemistry block of many of the Dewar flasks that we have, which is essentially like a thermos flask, double-walled vessel, which is sort of evacuated in between, so that we don't have any heat transfer to conductive or convective means. It's also silver on the inside, therefore you don't even have radiated heat losses or heat transfer. Because if you have a certain liquid like liquid nitrogen kept inside, it just stays there for very long periods of time. And Dewar was the one who did all this. And if you were to look at all the structures of benzene, there were peculiar structures. And then there were many other structures that were proposed. And there was one structure proposed by Dewar, and also called as Dewar benzene. Because of that prismatic structure which he proposed. Of course, that's not the main contributing structure for the properties of benzene, but it's well known and it's come to be known as Dewar benzene. So Dewar was, and James Dewar was responsible for all of this. Of course, in the other class I'm thinking there was a birthday tomorrow, and it happens to be birthday of Kamal Imams, who was the person who did to discover superconductivity in mercury. So it's quite nice that we celebrate Dewar today and then Raman tomorrow. Their work was sort of related. His production of low temperature liquid was in fact extremely important to the discovery of superconductivity, because he showed it in mercury at 4.2 Kelvin, which actually was produced by taking liquid helium. The essential technique for producing low temperature liquids came from Dewar. So that's basically what it is, and we know that sharing it. Okay, let's get back to the Raman scattering phenomenon. We said that if a photon hits the molecule scatters off, and the scattering can be at the same wavelength, in which case the molecule hasn't really exchanged any energy. You get really nothing out of this in terms of information about molecular states. But if the molecule scatters off the light at a different frequency, then the molecule has to be left in a different state. It could be a different rotational state, or it could be a different vibrational state. And if you then look at the frequency, the incident light and the frequency of the scattered light, that difference in frequency or the difference in energy thereof must really be telling me something about the energy states of the molecule. So if I have two energy states, and we won't even worry about what those are. Let's say this is state 1 and this is state 2, and if I shine light on this molecule basically is scattered by this light, and if it gets back the same frequency, then of course these two are of the same frequency, no information, because the molecule still resides in state 1. However, the scattering takes place in such a way that the incident light of this frequency, because what you observe is a scattered light of this frequency, nu prime, this nu, then nu minus nu prime must actually be equal to the energy difference between these two states, and therefore, if you look at the frequency of the incident light, of course you know what it is, and if you can measure the frequency of the scattered light, the difference in energy between these two photons actually tells you in what level you let the molecule in. It gives you information about the molecular state which has been accessed as a result of the scattering phenomenon. This is not an absorption phenomenon. It is not the molecule absorbs and goes to some state and then comes back to the state. It is not that. It's a spontaneous scattering process. The molecule is here, the photon itself scatters off, the molecule is there quivering in a different state. And you will see again that this has nothing to do with the dipole moment. It's got something to do with another property of the molecule. And that makes this whole process extremely different from what we have learned earlier. Now scattering, I don't know if you've studied this in physics, scattering depends actually on the inverse power of 4 with respect to lambda. 1 over lambda power 4 is scattering efficiency, which means shorter my wavelength, the more efficient is the scattering process. So if you want to do Raman spectroscopy and you want to see good scattering phenomena occurring, what would you do? You would choose a short wavelength. Long wavelengths don't scatter that well, and that's in fact the reason why the sunset appears so red. Because as the light passes through the atmosphere, so the sun has all the frequencies that you can possibly see, but then the short wavelengths get scattered off and they don't even reach you. Whereas the red, which is the longest wavelength that you can possibly see, is scattered the least because of this 1 over lambda power of dependence. Therefore, what you then see is this beautiful sunset. This is very spectacular in the evening, in the morning, because it can pass through a bigger column of the atmosphere, and therefore the scattering is that much more pronounced in these times. So the red basically is because of the fact that you're actually scattering. And that should leave you with a little thought that the more beautiful the sunset is, very bright red and very nice, it actually means you're scattering many of the other frequencies off. Probably tells you that your atmosphere is probably dirty. So the more beautiful the sunset, feel a little sorry for yourself. You're probably living in something that's not as clean as you think it is. The Raman spectra basically is that very same phenomenon. It actually has to do with the scattering of light by the molecules. Let's see how I can actually work on this. What I will do now is to, before I start showing the spectra and so on and so forth, let us see what this whole process really depends on. We drew this line, we said this goes to some state, and I don't know what the state is. It doesn't have to be a real state. This is only a model. Actually what happens is, here's the molecule, here's the photon, scatters off, you have nu1 and nu2. But if you want to understand this in some sort of a model, which you can later use quantum mechanics to describe for yourself, what you really do is you sort of pretend as if this molecule takes this light, goes to a state up there, which is not a real state really. Because the nice thing about Raman spectra is that you don't need to use light that is resonant with any state. In an absorption experiment, if the frequency matched the energy difference, you had an experiment going. If the frequency did not match an energy difference, there was no experiment, no absorption took place. In Raman, it doesn't matter what you use. You could use 240, 230, 280, 580, 670, anything. As long as the frequency is larger than the state you want to access, it's fine. So you pick that up, it goes to some state, it's not in a real state, we call that as a virtual state. The molecule is dropped back from virtual state to a level, and this is my scattered photon, and this is my incident photon. So if my incident photon is not this way, it is, let's say, this way, my scattered photon will be this way. In other words, the frequency difference between the incident photon and the scattered photon will always be the same as long as you are going from one state to another. If I am going from state 1 to state 2, and if I use photons of two different frequencies to begin with, my scattered photon frequency will change, but the frequency difference between the incident light and the final frequency of the scattered light, that difference will be the same, because I am actually jumping from state 1 to state 2 in both these experiments, which means I could use blue light and do the experiment, accepting that the scattered photon will be of a certain frequency, let us say lambda 2, and the difference here will be equal to the energy difference. Or I could use red light and do the same experiment. Experiment will still work, but I am not really constrained to use frequencies that match two levels. But when I do this with red light, the scattered photon will now have slightly different frequencies such that the difference is still going to be the same. So it essentially means that Raman spectroscopy can actually be done with any wavelength that you choose to do. And we will see how nice this advantage is a little while later. And of course, if I have a variety of levels, then I have a variety of scattered photons. Because in each case, I have this coming in, the molecule can come back here, So my scattered photon will have discrete frequencies at which you will be able to observe them, such that the difference between this and this is this difference, this photon and this photon is this difference, and so on. So we'll again see these repeats for the scattered photon. And by measuring the frequency of each of these scattered photons and knowing what your new incidence is, you can actually calculate the different levels into which you left the molecule as the experiment progressed. So all the rotational spectroscopy that we did earlier, all the vibrational spectroscopy that we did earlier, by an absorption process, you would actually repeat them by doing a Raman process. And sometimes experiments that did not work for you in the earlier case, you will see that it actually works for you with Raman. Give me examples of experiments that did not work for you in the earlier case, absorption experiments. Pure rotation, homonuclear diatomics. They gave you O2, gave you N2. You don't see a molecule giving you the spectrum. Why? No dipole moment. They give you N2 and ask you to record an infrared spectrum. You get an infrared spectrum. No, because there is no change in dipole moment as the molecule vibrates. Therefore, N2 or O2 will neither give you a pure rotation spectrum nor will it give you a vibration spectrum. It almost looks like there's no hope because you can't get these frequencies because the experiment just doesn't work with pure vibration or vibration rotation angle. So you really don't see them. HCl, yes. Carbon monoxide, yes. All these will give you data. But homonuclear diatomic molecules, by which I mean diatomics in which both the atoms are the same, homonuclear, they really don't give you vibration rotation spectra or a pure rotation spectra in an absorption process. But in this process, as I said earlier, it is not the dipole moment that is important. Actually, what is important is polarizability. In the scattering process, what is important is polarizability. And what do I mean by polarizability? I simply mean that if I had a molecule, or if I had a bunch of electrons, electron cloud, and I applied an electric field across it, what happens to this cloud? This cloud will get distorted. So if I have, let's say, an electron cloud out here, and then I put two electrodes, plus and the minus, that is capacitor, then this, being a negatively charged species, would want to distort itself in such a way that it would try to do this, so that it reaches out for the positive electrode. And the extent to which this happens, or the ease with which this happens, is what I call as the polarizability, the ability to polarize. So if I take, for example, a hydrogen molecule, and let's say I take fluorine, and let's say I take iodine, two atoms in the same group. Put these two atoms between two electrodes, apply the same electric field. The sense that apply a potential, a certain voltage, distance is fixed, so V by D will be the field that these molecules will experience. What do you think will happen to the electron cloud in fluorine and iodine? They should distort. If you assume that they were reasonably spherical, they are not really, because they are a P5 system. But then the electron cloud will sort of polarize itself and try to reach out for the negative, for the positive electron. But who do you think will do it better between fluorine and iodine? Iodine. The larger molecule has a greater polarizability, and therefore the electrons in iodine, which are quite far away from the nucleus and therefore are not really under a leash, would tend to polarize much better. And therefore you say that the polarizability of iodine is much better. This is what you really need. So the polarizability is a more complicated situation than a simple dipole moment. Dipole moment is a vector, whereas the polarizability, you read about it as a tensor. Maybe a little while, sometime later, I'll tell you what you mean by that. Let's not get into that situation. All we are going to look at now is that the polarizability is essentially a property that tells me how easily I can distort the electron cloud in the atom or molecule on the application of the electric field. Either you can apply the electric field by putting two electrodes, or if you shine light, the electric field of light will do the job for you and try to displace the electron cloud as a function of time when the electric field actually oscillates as it passes through the system. The question before us, what about this polarization? Now let's say I take the H2 molecule, and let's look at the vibration of the H2 molecule. Starts at equilibrium position, it goes out, comes back, and does this. And we know, we have seen this before, that there is no change in dipole moment. The dipole moment actually turns out to be zero all the way through, and that's the reason why this molecule is not vibrationally active in the earlier thing that we studied. But now look at the polarizability of these electrons as you change this internuclear distance during a vibration. You start from here, a certain distance, and the electrons are under the influence of the nuclei. But as it extends itself, what happens to the polarizability? Will it become easier or difficult? It will become easier, because now the two nuclei are quite far away, and the electron cloud really isn't under that much of a control of these two nuclei, and therefore the bond that is there between hydrogen now contains electrons that can be possibly more easily distorted on the application of an electric field, as opposed to the situation where the two nuclei are quite close. So as I pull it out, polarizability has increased. I come back, I get the original value, and then when the molecule compresses, the polarizability actually gets back. Therefore, as the molecule progresses, while the dipole moment is not changing, what is changing? The polarizability certainly is changing. And therefore, you will find that this molecule has a polarizability that changes with vibration, while the dipole moment is not changing with vibration. So, which therefore means, as the polarizability is changing with vibration, if you apply an electric field and you induce a dipole moment, that's what polarizability is all about. That is, if I have two species and then I apply a field and I polarize the electrons to move one way or the other, what have you done? You have actually induced a dipole moment in the system. So the polarizability is therefore related to the induced dipole moment. So if my polarizability changes with vibration, on the application of an electric field, what is going to change? The induced dipole moment is going to change as a function of vibration. The permanent dipole moment does not change, but the induced dipole moment changes because of the fact that the polarizability changes. Now when polarizability changes, scattering is a phenomenon that you will see. In other words, the hydrogen molecule will not give you a spectrum in pure absorption because the dipole moment is not changing. But the same hydrogen molecule will give you a scattering process going, simply because the polarizability of the hydrogen molecule is actually changing as a function of vibration. In other words, hydrogen molecule is infrared inactive in absorption, but is actually active in a Raman experiment. So you can take hydrogen, shine light on it, and look at the scattered photons, and you will be able to see scattered photons that are giving you information about the rotation levels, about the vibration levels of this molecule. Information that you could not get earlier by a simple absorption process. And that's the nice thing about Raman. Many other systems you could not study earlier. They actually become accessible to you when you do a Raman experiment or when you do a scattering experiment. Because the main difference is one depends on dipole moment, one depends on polarizability. Dipole moment does not change for these molecules, you can't see them in absorption. Polarizability changes, and therefore you will see them in a scattering experiment. Therefore you use the language that a hydrogen molecule is Raman active.
Is there any molecules which don't respond to Raman?
Oh yeah, we will see that. There will be molecules that will have no Raman, it will be Raman inactive. It's possible. Let me just get to that situation. Carbon dioxide, in fact, has one vibration and Raman inactive. And we will get to that situation, we will get to that point. As of now, this molecule is Raman active. Take the carbon dioxide molecule, which will eventually answer the question that she has asked. When this carbon dioxide molecule does this, the symmetric stretching vibration, any change in dipole moment? No. And we knew that, we already have seen that this stretching vibration is not going to be seen in a typical infrared experiment. But what will you see in an infrared experiment? The antisymmetric stretch. Because that changes the dipole moment as the vibration goes along. The bending changes the dipole moment. So if you record a spectrum of carbon dioxide, you will see the antisymmetric stretch, you will see the bend, but you will not see the symmetric stretch. But what happens to the symmetric stretch in terms of polarizability? Here are oxygen atoms, the carbon in the center, and as I pull it out, the bond length increases, therefore the polarizability has to get better. Therefore you will find that the carbon dioxide molecule, the symmetric stretch, which could not be seen in an IR spectrum through an absorption process, can actually be seen in a Raman process because the polarizability is changing with time, with vibration. And therefore you will find the carbon dioxide symmetric stretch will be seen in a Raman experiment. So it's not all lost. When you say that there is calculation tells me that you have a symmetric stretch, but I can't see this in an experiment, so how do I really confirm that such a vibration can actually occur in this molecule? You can't see it in an absorption experiment, but you can see it in a Raman experiment, simply because while there is no change in the dipole moment of the molecule, there is constantly a change in the polarizability as a function of vibration. And therefore, this molecule of vibration, the symmetric stretch, do a Raman experiment, a scattering process, you will see a transition occurring from V0 to V1 of this antisymmetric stretch. The symmetric stretch. Now go to the antisymmetric stretch. What happens to the antisymmetric stretch? While one has decreased, the other length has increased. So what has happened to the polarizability of one bond? This bond has actually increased its polarizability, while this bond has actually reduced its polarizability. And the net polarizability of the molecule, if the phases are all right, actually doesn't change. So here the certain polarizability increases and decreases, this one increases, polarizability is greater here and now less here. The net polarizability for the molecule hasn't really changed. So as this molecule is going back and forth, these two are basically compensating each other. And when they compensate each other, you'll actually find that there is no net polarizability change, and therefore the antisymmetric stretch of carbon dioxide, which you will very happily see in an infrared spectrum, in absorption, you will not see it in Raman. Simply because the polarizability change is not really occurring as a function of vibration. What about the bend? It's not so easy to visualize, but let me tell you that the bend is actually infrared active. Actually doesn't turn out to be Raman active. The polarizability change again is lost, and therefore you will not see the bend showing up and down, because there is no change in the polarizability in the system. It's not so easy to visualize in the case of the bending system, it's more easy to visualize in the case of the. Let me put forth a rule to you right now. Later we will see by drawing some polarizability graphs as to how this can be